Um, you're warned that this is being recorded. This is a picture of the University of Massachusetts Amherst, where I'm coming from, on a pretty fall day. I hope you all can visit at some point. I'm going to talk about simulating flash boiling nozzles. This is a lot of work from over the years involving a lot of people, including Dan Duke. All right, so coming back to the University of Massachusetts, we are the main campus of the UMass system. And oh, how about that? There we go. We're located about 2 hours west of Boston, here with the red X, about 3 hours north of Massachusetts, if you ever want to get out there. It looks like this in the fall with the pretty colors. The other thing I'll point out, our school's about 32,000 students. The population of the town is not much more than that. Okay, so I do owe acknowledgement to lots of folks who've helped work on this and over the years, and this is their current locations. With the exception of Dan Duke, everybody's affiliation at the time they worked on this was UMass, but it's maybe more interesting where they've gone now. So let's talk about some background, why this is an interesting problem. Now, I made a lot of these slides on the plane ride over, and at the time that I was flying to Australia, I was not aware that Australia has no nuclear power plants. So this is not such a motivational slide for Australians, perhaps. But if you live in a country that had a serious nuclear accident, like 2 Mile Island, this might be interesting. And the idea would be, if you've got a pressurized water reactor with a large break and you've got a LOCA, a loss of coolant accident, you could end up with your core uncovered. The rate at which you lose coolant is the rate at which you have to replace coolant to keep your core covered. And when I was a grad student, my advisor was a nuclear engineer. So this was his motivation. It, to be honest, wasn't exactly my motivation, but sometimes motivations differ. More motivation comes from those interested in the automotive world, where you might have a fuel injector, and this is fuel injector directed at you or the hole's directed down, and you've got this needle valve that opens and closes to shut the fuel off. And about 20-something years ago, as new injector technologies began to be used in gasoline engines, it was discovered incredible temperature sensitivity. So if you're patternating your spray, just taking a collection of what's coming out, at 20 degrees C fuel temperature, everything looked what you'd expect from an fuel injector. And by 90 C, your fuel's actually in the center here. And this is a side view showing this collapse of the individual sprays into single spray that was not desirable, and it was very uncontrolled. So again, flash boiling seems to be the operative phenomena here. Now I've deceived you long enough. The actual motivation is just my advisor walked into my office and says, "Can you do it?" And I didn't really know what I was getting into. I said, "Yeah, sure. I can try and," you just want to know, could I simulate flash boiling? He's like, "You do cavitation, that's a phase change, right? You do CFD, right? Just make it all work." And at the time, I was living in a world of thermodynamic equilibrium. And I'm going to try to make the case to you that certainly with flash boiling, equilibrium assumptions are not appropriate. So I mentioned 1996. You couldn't just Google things back then. You had to walk over to the library and to figure out what actually flash boiling was. So just to show you on a pH diagram, so here's pressure, here's enthalpy, and here's the saturation dome. think of it this way. If you've got some sort of nozzle flow in a high pressure upstream condition, that's state 1, you'll drop down through the saturation curve, saturated liquid would be state 2, into the vapor dome. If you're flowing through a nozzle or an orifice or a crack in a pipe, you're not doing any work. We'll assume adiabatic. So enthalpy stays constant, except for a little conversion to kinetic energy, but total enthalpy stays constant. And so you're working mostly on this vertical line. And two things, if I'm going to illustrate what happens on the right-hand side of the figure, have to occur for this phase change to proceed. So one, see these black arrows outward? You have to have a velocity divergence. If you're going to grow a bubble, that requires positive divergence in your velocity field. The second thing is the red arrows indicate heat transfer in. This is, on a macroscopic sense, adiabatic phase change. But of course, on a microscopic scale, that doesn't make sense. The liquid's going to have to give up heat to provide the enthalpy of vaporization. And I just want to make the case this is a hard problem. And so I'm going to jump ahead and actually show you a few results just to show the complexity of what we're going to run into here. So this is a nozzle. Flow is from your left to your right, indicated by the red arrow, and it's axisymmetric. So I'm showing you density on top half of the figure and velocity on the bottom, the velocity magnitude. And this is just hot water being discharged. So the first thing to note is density starts out about 1,000 kilograms per cubic meter, like you'd expect, and it drops precipitously near the exit. Meanwhile, with that density drop, you've got a tremendous acceleration. Nothing really is interesting happening until you get near the exit, and then boom. And you can see how incredibly wide the jet is here. We follow the edge of that high velocity zone. So when this fluid is coming out of the nozzle, it's just exploding into a wide jet. And so there's a few things. If you sit down and say, well, maybe I'll try to treat this as equilibrium fluid dynamics. Let's assume the density is in equilibrium. Punch up the numbers with your calculator. Say, I know my m dot, I know my mass flow rate, what's my average velocity? You come up with something huge and ridiculous, like 1,000 meters per second, or something, depending on the conditions. This is very high. So this is not a situation where you can get away with assuming thermodynamic equilibrium, which would correspond to a relatively slow transit time through the nozzle. It has to be slow enough for the fluid to exchange heat to get to equilibrium. The other extreme that's back in the early days that was considered was the frozen flow limit, where flow through the nozzle passage time so short, you don't have time for phase change. And you're just going to assume that the thermodynamic state is unchanged until you get through the nozzle. And neither extreme seems to work. And so we need to come up with some finite rate phase change model. So we're in the unhappy middle. Just to show you an example of where some of these assumptions lead you. This was an experiment done by Rolf Rates, these black symbols. We have mass flow rate in water through a nozzle with temperature, and it drops. And I don't show it with the circles, but eventually it plummets once it gets hot enough. Thank you. So if you assume frozen flow, you have no real temperature variation of flow rate because you're assuming that the thermodynamic state doesn't have time to change. If you have equilibrium, it just drops off. And if you use a model I'm going to talk about, you get it just right. Now, where does this model come from? How do we choose our equations? Well, the source is a little surprising. Albert Einstein. So Einstein, before he got sort of lost and misdirected into relativity, he worked in two-phase flow. He worked in refrigeration, for example, and published papers about wave speeds through dissociating gases and other cool things. Unfortunately, he published these in German, and my German is not really good enough to decipher it. So Bilicki and Keston, who I guess could read German, published this idea in 1990 that we can have a finite time relaxation model that goes a bit like this. So just to define symbols, X is going to be the quality. It's going to be the mass fraction of vapor. And then it's going to approach X bar, the equilibrium mass fraction of vapor, just using a form like this. And this shows up in a lot of branches of physics. It's common, and you can work something like this out with a truncated Taylor series. But the idea is that the difference between our instantaneous vapor fraction and the equilibrium vapor fraction drives the rate of change of that mass fraction over some time scale theta. Theta is not a constant, it's a function, and we need to figure out what that function is. So this was the idea attributable to Einstein. Bilicki and Keston came up with the idea you could use it for two-phase flow. And then just about a few months before I started this, these researchers in Poland came up with a correlation for theta based on the Moby Dick experiments. And that's just a great name for these experiments. There's a long straight tube of hot water. That's all it was. And we vary the upstream conditions, and using gamma ray densitometry, these folks measured lots of thermodynamic state variable. Well, mostly they measured the quality as you discharged, and you made lots of steam, kind of like a whale's blowhole. And that's why it's called the Moby Dick experiment. All right, so that's all good. This is, however, requires a little more explanation. So that timescale theta, this is the correlation that they came up with, where theta naught's a modeling constant. And you've got two other modeling constants there, that's minus 0.54 and minus 1.76. Now with, I think it was von Neumann said with 10 constants, I can curve fit an elephant, or 8, I think. We've got 3. Let me explain the other variables here. Void fraction. So this time scale is very, very large. So phase change is very, very slow if I don't have interfacial area available to me. So once you first make a few bubbles, now you've got more surface area. And as you make more surface area, it can go faster. That's what that alpha term is, alpha being the void fraction. And then this is the dimensionless temperature from PSAT. So when you're in equilibrium, your pressure should be the saturation pressure. So this Greek variable, psi, it measures phi or whatever the hell it is. It measures how far you are from PSAT. And as you get closer to PSAT, things slow down. If you're farther, you go faster. And my contribution to all this was to build a CFD code around it, to go from this 1D concept to 3D. At the time, there was only one existent multidimensional, that was 2D, flash boiling simulation in the literature that I've ever seen. And it's some paper that nobody ever read or cited. Perfectly good paper, though, just didn't get discovered. Anyway, so if you're going to make yourself a CFD code from that correlation, you need to update all your variables. Density, you'll update from conservation of mass. Velocity from momentum, that's all standard. The tricky part is, how do you take that transport equation for mass fraction of vapor and get pressure out of that? Because you need pressure. You also need something that'll work when there is no phase change, because sometimes during part of a calculation, you haven't got phase change. So you need to collapse back to some reasonable, incompressible, or low Mach number formulation. So the way you do it is you use the chain rule to convert a change of X to change of density. Once you've got your change of density expression, use conservation of mass to say, okay, that's a certain velocity divergence. Remember our picture of a bubble? There's a velocity divergence required to change phase. And then pressure projection, you take the divergence of the momentum equations, will give you a Poisson equation with some extra nonlinear terms that represent the phase change. And this is important, this construction. It's kind of an oddball construction because you need very close coupling between the phase change model and your pressure equation. If you try to lag anything, if anything is not implicit, you just don't have a stable code. And I generated a lot of unstable code until we figured this out. A word about software engineering, because that's a passion of mine. Originally, because it was the 90s, I wrote a 2D code in Fortran, but later ported it to OpenFOAM. And just a one sentence plug for OpenFOAM is that I started with compressible liquid transport code, and I just changed some lines and made it a flash boiling code. And the reason that works, the reason it's so efficient, is two different CFD codes, your compressible liquid code, your flash boiling code. A huge amount of the infrastructure is the same. Exactly the same. The stuff that reads the inputs, the stuff that writes the outputs, that calculates cell volumes, it's all the same. By analogy, we think of ourselves as being very different from carp. But most of our source code is the same. Change a little bit, you go from carp to person and possibly back again. So CFD codes actually have a lot of underlying similarities. And when you work in OpenFOAM, you get a lot of nice capabilities. In addition to the flash boiling and cavitation, you can work in 2D and 3D. It's parallelized, generating polyhedral meshes. And then we added some others. And I needed to find this term non-condensable gas. We've got liquid and vapor. The vapor is a gas. So if I have water, I have water vapor. But I'm often injecting or spraying into some, say, nitrogen or air. To distinguish that downstream gas, I call that non-condensable gas. So you'll hear that. Compressibility is important. In a two-phase mixture, the speed of sound can be very, very low. I say low, speed of sound of 30 meters per second. I haven't tried it, but I've often suspected if you had a big pile of shaving cream and drove through it with a car, you could hit the speed of sound in the shaving cream. And it's because if you think of speed of sound as a delta P over delta rho, the delta P is dominated by the more compliant phase, the squishy one, and the rho is dominated by the dense phase. So we also have some other features we added, like sealing. If we're dealing with valves opening and closing, you have a topological problem where you abruptly go from having, say, two separate domains into one as this valve opens. So we have an algorithm to make that a more gentle process by adding some imaginary forces. And we have boundary and mesh motion because, again, you have surfaces that are moving. And I'm not going to talk about the details of that. So I mentioned for applications, loss of coolant accident, nuclear reactors, gasoline injection, direct injection, pulse meter dose inhalers. That's what Dr. Duke works on. So a lot of you know about that. Cryogenic propellants, liquid oxygen, liquid hydrogen, for example, are used in rockets, and these can be flashing, right? They're super cold, and they're often very high pressure. Refrigeration. So in most refrigeration systems, you've got a throttle. It's just an adiabatic little orifice where your liquid drops in pressure through it and vaporizes. The Joule-Thomson effect means that you end up with cooling. Well, one thing Australia is very, very good at is cold spray additive manufacturing. I don't know if anybody here has an interest in that, where you have this black inner nozzle. This is a converging diverging nozzle where you've got helium going at 1,000 meters per second. and accelerating metal particles so fast that they splat like putty against the substrate, and you can 3D print very nice objects. So that's actually, Australia is a world leader in that technology, but those nozzles clog. At 1,000, well, the particles don't get up to 1,000 meters per second, but they get going fast and they hit the nozzle walls and stick to it. And pretty soon your expensive tungsten carbide nozzles clog. So if you make a device like this, throttle CO2 through it, you make your cold spray even colder and the nozzle doesn't clog. That's an example of Joule Thompson core. I actually got a patent on this last year. All right, so we really have no expectation that when you take a correlation and use it beyond the bounds of where it was intended to be used, you should have no expectation that it works, right? It's one of those things that we always caution students about. You find a correlation designed for here, you really wish you could use it over here in this regime, you can't. So anyway, let's go ahead and do that and just see if it works. Maybe we'll get lucky. So let's show you some 3D cavitation validations. Not that that correlation was ever intended necessarily for cavitation, but what the hell. This is for a gasoline surrogate. So that correlation was for water, so completely different fluid. This was done by Dr. Duke back when he was at Argonne National Lab. And so the idea was use this gasoline surrogate going through a channel. Channel's got some sharp inlet corners, so the flow separates off those corners and cavitates. With a nice X-ray source, the advanced photon source, you can image this. It's a line of sight diagnostic, but it gives very nice results. And here is an example of the computational results, just showing for a line of sight how much vapor would be in that along that line, and two different views from the experiments. You take one and you rotate things 90 degrees and look the other direction too. And I didn't label these because I think it's kind of fun. How do you recognize which one of these is the computational result? The computational result is the one without the defects, right? It's the top one where you have symmetry. But it's I think for something being used out of spec, it's pretty good. This is swirling hexane flow, where you've got these 4 swirl ports. Flow comes in, swirls around like this, comes out, and spreads out into a hollow cone spray. If you have an oil furnace, there's a pretty good bet there's a nozzle like this inside your oil furnace. And we compared these black symbols here are experimental measurements for the spray angle as a function of temperature. And we compared our model simulation results to that. It's in the ballpark, it's not perfect. Then this is a cryogenic application, refrigerant 404A. So this was in collaboration with the University of Warwick. They wrote their own code and OpenFOAM using the same HRM model, and I helped them. And then we added some machine learning because that's what we do these days. The machine learning is really tangential this, but again, comparing to some velocity experimental measurements for the refrigerant, not bad. And then for gasoline direct injection, to validate there, this is a injector like I showed you in the early slides. The fuel's isooctane, so now we have a different hydrocarbon. And 2 different conditions, G and G2. The upstream conditions are all the same between these two. It's the downstream conditions that are different. In spray G, the downstream pressure exceeds the vapor pressure, meaning you're subcooled. If you make some vapor, it'll to some degree recondense. But G2, the downstream pressure is less than the saturation pressure. Saturation pressure in this case is about 85 kilopascals. So G2's flashing conditions. And we got the geometry and the motion of the needle. Again, this is something Dan Duke had a hand in from X-ray imaging at Argonne National Lab. So to orient you, this ball valve lifts up and the flow comes around into these holes. Notice the holes are stepped. So counterboard from the outside. The automotive industry did this because they hoped that it would act a little bit like a shorter hole. They don't really know why they did it exactly. I asked people, they just did it and it seemed to work. But we'll come back to that. But with the X-ray measurements, we have this valve, and the motion of this ball is a little more complicated than you think. You'd expect it to lift up. That's the intent. But it also wiggles around in various directions. So we compared to mass flow rate measurements, transient ones. So let me show you this plot first. So here on the x-axis, notice the time. And look on the right, blue. This is the needle position. So the needle lifts about 50 microns for the most part. It actually slams up, bang, and then hangs out around 50 and then drops. So we then we have experimental measurements of the mass flow rate, this black line. And that mass flow rate is quantified here on this left axis. Now, a few things to note. See this big spike here? That's probably not real. That's an artifact of the strain gauge involved in picking up the mechanical slamming of that ball. But we get a good match on the simulated rate of injection. And you can either include wobble or not include wobble, and you get the same answer. But the other thing too, you get exactly the same mass flow rate, whether it's the non-flashing conditions or the flashing conditions. If you look at the legend, changing the downstream pressure had no effect on the mass flow rate whatsoever. So there's a word for that, right? Choked. So that was interesting that these are choked. And then this is just some additional validation. So the experimentalists did some long distance microscopy under flashing conditions and non-flashing. The important thing to note is the flashing sprays are bushier, they're touching, they're completely filling that counterbore. The non-flashing are narrower and there's a little bit of gap in there. And we were able to capture this in the computational results. The flashing ones or sprays are bushier. The non-flashing, there's some distinct space between them. So again, that 1D correlation for water is working better than we ever hoped. And we didn't change any of those 3 empirical constants in it. There's no curve fitting here. So I don't know why it works so well. All credit goes to Albert Einstein. The other thing that you notice, especially towards the end here, there's a lot of wiggling in these sprays, both the experimental and the computational. What's the source of that? I'm going to not answer that yet, but about 10 slides down, we're going to come back to that. So remember the oscillations. Now, it would be remiss of me if I only showed you good results. So right here is the worst result I've ever gotten with this model. You might say, well, it looks kind of about the same shape. Maybe the experiments are a little wider than the computational. But here's the ugly part. The experiments are using this axis, and the modeling results are using this axis. Factor of 10 difference. I have no explanation what went off the rails here. It's isooctane, the same fuel I was just showing you that looked okay. Remember, we nailed the mass flow rate. How can you be off on a fact? This is just a slice measuring density 2 millimeters below this. How can you be off by a factor of 10 and still on density? So it's an average density. So it's really an indication of fuel concentration. How can you be off by a factor of 10 and get the mass flow rate right? Unless you're off by a factor of 10 in the velocity, exactly the other way. As soon as the experiments get fixed, we'll be good. But so, I don't know. And what's even stranger is here is a analogous measurement. So this again is this is 0.1 millimeters downstream of a different injector. This is a diesel type injector, single hole. And the experimental measurements of the projected density reasonably close to the simulations. I mean, it's a slightly different fuel, a slightly heavier hydrocarbon, and it's a single hole spray, but you know, this time it worked. So I don't know. All right, just a little more validation. This was not done by me. I'm not an author on this paper, but General Motors funded the work. So they got a copy of the code, they ran it, they teamed up with Shanghai Jiao Tong University and did experimental measurements with the single hole and measured how the spray widens as a function of the ratio of ambient pressure to the saturation pressure. So here's the important number one. To the right of this, the ambient pressure exceeds the saturation pressure and you're not flashing. To the left, you're flashing harder and harder and harder, spray angle goes up. And the way they compared this is they did some line of sight integration through the computational results to try to mimic what the backlit photograph would look like. So there's a little bit of optics simulation in this paper that SJTU did from the CFD. So I thought that was a nice wrinkle. Okay, so that's validation. It offers, with one exception, some credibility to this approach, but also in itself, it is fascinating that for some reason, this correlation for 1D steady state water flow is working for cryogens, cryogenic refrigerants, gasoline, and heptane, etc. All right, that's not, I think, the interesting part. The interesting part are some nozzle physics. So I want to talk about what happens as we ratchet up the pressure. I'm assuming ratchet up the temperature. So this is a nozzle flow from left to right. Because this is axisymmetric, just in your mind, rotate these results around this line of axisymmetry here. Right, just rotate it around that. So this is the nozzle wall, that boundary. Flow's going from left to right, and it separates off this corner. These ISO lines are pressure. These are ISO bars. And the gray scale indicates density. So the black is where vapor is. So you get a separation off this corner and vapor all the way through, and you have all the pressure drop across the inlet. This is what you expect from a nozzle. This one is weakly flashing. You're discharging into atmospheric pressure. So any temperatures above 100 C, that's superheated. So it looks like what you expect from the top, similar to cavitating nozzle. But as we start increasing the temperature, so compare this to the bottom, now the pressure drop has shifted from here to here. Notice the isobars. So this straight flow, you're getting a density drop and an acceleration. So it's completely different. This helps explain some of the explosiveness of this these fluids coming out of the nozzle, because you get these isobars piling up at the exit, big pressure gradients. And that's a consequence of the phase change. So we can look at these results another way. Let's take a line that goes down the center of the nozzle, and we'll non-dimensionalize everything. So 0 is the entrance to the nozzle. This to the left is before you get in the nozzle, to the right is within the nozzle. And a constant density flow would look like this. And we non-dimensionalize the pressure. So 1 is the upstream pressure, 0 is the downstream pressure. So you come in, big acceleration of the inlet, you overshoot and go below the exit pressure. Why? Because of that separation creates what's called a vena contracta, a narrowing down. And the area that's actually used by the liquid coming in is 61% of the nozzle area. It's theoretically pi over pi plus 2. That comes from an ancient mathematical technique called conformal mapping that was used for solving inviscid flow problems. This was published in 1903 by von Mises. Another paper in German that I didn't read. So you have an adverse pressure gradient. If we ratchet it up to 75 degrees Celsius, we're still subcooled, but now the vapor pressure puts a floor on the pressure in this nozzle. So it comes down to that vapor pressure and sits there, and then it goes up at the end. And if we get really hot, we sit at the vapor pressure. It's an attractor, that vapor pressure, and then kaboom at the exit. Explosive pressure gradients. So that's kind of amazing. It does. And when we use stepped holes, we get even stranger physics. So this is one of the holes from one of those fuel injector simulations. And alpha is the volume fraction of vapor. So this might look kind of what you expect, but it was not what I expect. And I'll explain why. So if you think of a free jet, if I just have an orifice with a jet coming out, I expect that jet to be at the ambient pressure, right? If I have a garden hose and there's a water jet coming out, all those streamlines, they're going straight. There's not a lot of streamline curvature. So there shouldn't be a lot of pressure gradient. So if it's 1 atmosphere over here, should be 1 atmosphere all through my garden hose spray. There's not a lot of excitement to generate a pressure gradient. But you can see there's a lot of vapor here. And we couldn't figure out where that vapor was coming from. And we looked at pressure. This is pressure. Downstream here, we're 6 times 10 to the 5th pascals. Right? So 6 bar down here. In this step, you're at a much lower pressure than down here. And we could not figure out why. Why that would be. Why you can maintain a different pressure. So we finally decided it was a compressibility effect. And this is what we said, that the persistence of the vapor into this region, it's not condensing. It's not what one would expect from simple nozzle discharge into an unbounded region. It appears the counterbore is further expanding the two-phase flow, analogous to a divergent nozzle promoting supersonic conditions. So this is acting like the diverging section of a de Laval nozzle. And continuing to expand this flow, drop the density. And we published that in 2015. And that is as much as we said about it for lack of courage. Because we're sure this was right, didn't fully understand it, and we were afraid to say too much in case we embarrass ourselves because it was wrong. But finally, some people came along about 2 years later with a lot of guts, a lot more courage than we had. And they're from the University of Melbourne, Josh Lacey. 2 years later, was studying these stepped holes. So now everything's flipped upside down. Here's the stepped holes discharging out this way. And he very confidently ascribed this to underexpanded flow that undergoes a rapid expansion. So he understood all this and published a beautiful experimental paper on this. And I was always embarrassed that without the benefit, in CFD, I can see all the fields I want. I can see pressure, I can see temperature, I can do speed of sound. I can see all that. An experimentalist who can measure maybe 2 quantities just analyzed it beautifully. So very nice achievement. So after seeing that, we said, all right, let's look at this a little further. So let's look at the pressure. And this is just non-dimensionalized by the stagnation pressure versus your distance down the hole. So 0 is just upstream of the orifice. This triangle here is the exit of the counterbore. That's the exit of that stepped region. We did it for flash boiling conditions and subcooled conditions. So here, the downstream pressure is 2.76 times saturation pressure. And here, that ambient pressure is about 1/5 saturation pressure. So, and what we can see is that here, you're continuing, your pressure is on its way down through the, as you exit the hole, and it continues to diminish. So you're not acting like a free jet, you're acting like an underexpanded jet, transonic one. Remember the speed of sound being, only 30 meters per second in a bubbly flow? It varies a lot with the volume fraction, but and this is the subcooled. So here pressure goes down below the ambient, pops back up like you'd expect from an overexpanded nozzle. But the cool part is this is with a phase change. So this is a condensation shock. So yeah, basically once Josh Lacey had showed us the way, we analyzed the hell out of it. But we then came up with the question, can we correlate this behavior? Is there some simple rule of thumb? So we ran 100 cases with various thermodynamic conditions and geometries, used a design of experiments matrix to guide us on this. And we found that we could correlate the behavior. So this is the plume half angle versus, in non-dimensionalizing, everything's a time scale. So I'll explain what this tau is. But the blue-green symbols are the sprangle you get from a straight hole, and the red are the sprangles you get from a stepped hole. And what you see is for large values of tau, you're getting enormous spray angles. Right? Half angles of 50 degrees, that means it's 100-degree spray under certain conditions. So you really have the opportunity with that whole geometry to manipulate and control the spray. So that, in the industrial world, we live in academia, we just want to understand it. But in the industry world, they want to control it. And if you want to control it, you now have a way. It's just, what is this time scale? So it's the ratio of the transit time through the nozzle divided by the time required for phase change. If you have a large value of tau, then you have a relatively rapid phase change and longer transit time. In other words, if you have a large value of tau, you're giving it lots of time to change phase. If you have a small value of tau, you're rushing it through. So this is more like the equilibrium limit, and this is more like frozen limit. So it's pretty obvious that you can estimate the transit time just by taking the ratio of the length divided by u. the velocity. The phase change time was a lot harder to estimate. So in a sense, we used some circular logic, which I apologize for, but we took that correlation for phase change rate. It's in our code. And we just evaluated it under equilibrium conditions for the volume fraction. So this is volume fraction, remember, and this is dimensionless pressure, P minus P sat, non-dimensionalized. So we just put in the downstream conditions for that. And we're able to correlate with R squareds over 0.9. Now, to be fair, we're correlating CFD results that came from that very same expression. So let's not get too excited. But if this is right, this could be very useful for those of you who want to use stepped holes to manipulate these springs. All right, three-dimensional effects. Do you remember we were looking at the fuel injector spray and we said, why is it wiggling? Those sprays were dancing around. That turned out to be an interesting little side subject. So here is a slice through that domain. The colors are showing average density and the streamlines are colored by velocity, which really isn't that important. So what's to notice here? A couple of things. Notice the streamlines start swirling around before they go in the hole. And notice on the left, we have really what you'd expect, right? Nice jet coming through, boom, straight. But on the right, there's this swirl, and the red, the dense liquid, it's forked. It's bifurcated. Notice that there's vapor in the middle and it's fuel on the outside of that. So what's going on there? Here's an instantaneous snapshot. So what we found are very strong vortices forming. And the snapshot just shows isosurfaces of pressure and again streamlines. And you can see these vortices, they do various things. So they can start in one hole and connect to another hole. Occasionally they just end, get weaker, that's rare. And then they can also come and, like this guy here, end at a surface. I'm not showing you the surface it's ending at, but trust me, it's ending at the surface. So I think it was Lord Kelvin came up with the proof that vortex tubes can't terminate in an unbounded and viscid fluid. It's a long time ago that I studied that, but it basically means these vortex lines don't usually just end. They either go out two holes or they'll end at a surface, because Lord Kelvin didn't have walls in his theorem. And they dance around. Very, very transient. They tend to live for about 10 to 80 microseconds. But what they do, so here's, we snap this still of a very heavy rotation in one of these holes, very brief, but all the liquid goes to the outside. And you have this center, this vapor. So the colors here are vapor volume fraction. So all the liquid's spinning on the outside, and you have this vapor, and it can connect to another hole loop. And when it does that temporarily, it makes the spray angle really wide and changes its angle. It dances around, gets very wide. And here's another slice. You can see one hole doing the normal thing, and over here, it's gone swirly. And where's that swirl come from? It comes from the proximity of the surface to the hole. When you've got a hole, and so here's a hole, and you bring a surface down close to it, the flow in that hole starts to swirl. It's been observed experimentally. I'm not exactly sure why that axial vorticity starts getting accentuated by that, but it does. And then let's talk about fluid composition effects. One last thing here. So gasoline ethanol blends were of interest for quite a while. And gasoline and ethanol don't form ideal mixtures. They form what's called azeotropic mixtures. So that means the properties like vapor pressure cannot be expressed, cannot be calculated with any simple averaging. So over here on the left side, we have no ethanol, all gasoline. And on the right side, it's all ethanol. So gasoline here, ethanol here in between the mixture. If you look at the hot curve, 60 degrees C, you'll see at about 20% ethanol, vapor pressure higher than either pure phase. No averaging can get you there. So you have to use activity coefficients and lots of other nasty stuff to try to calculate those mixture properties. But you can do that and put it in the code and then see sensitivity to ethanol concentration. Wide sprays here with E60, narrower with E85. And just recently we looked at methanol in these fuel injectors. You may have heard of the concept of an e-fuel. Let's take excess renewable energy. Instead of storing it in a battery, use it to synthesize a high energy density fuel. And that's the medium of storage. And then liquid fuels are awfully handy for propulsion. But if you try to put in methanol instead of isooctane, you've got a lower heating value, or you can compensate by just injecting longer. But there's a very different propensity to flash. So we looked at 3 cases, isooctane at 363 compared to methanol at the same temperature. But there's very different saturation pressure. So we also looked at hot isooctane. So it had the same saturation pressure as the methanol. So the question is, when you have the same saturation pressure, do you get the same flash boiling? So what to notice? Isooctane is light blue here. This is non-condensable gas concentration. So we're just defining our spray as where the non-condensable gas is not. Light blue versus dark blues. What this means is the methanol pushes all the surrounding gas out, while the isooctane doesn't. Hot isooctane is looking a lot like methanol in that regard, right? Same spray width. Where we matched PSAT. But one thing, if we look at the equilibrium mass fraction, it's completely different. And the difference is, and this is one message I want to leave you with, the flash boiling is not all about PSAT. This is a consequence of the very different enthalpy of vaporization. Methanol's got 4 times the enthalpy of vaporization. And so one consequence of that is whereas, so the injected fuel was 363 Kelvin, whereas the isooctane stays pretty hot in the spray, the methanol gets cold. Totally different temperatures. We can see that quantitatively. So on the left, you've got temperature, the green's the methanol that gets cold. This is just a slice, 2 millimeters down. And this is the amount of non-condensable gas in that slice. And you'll see the isooctane when it's hot and methanol occupy all the space. So you either got liquid fuel or fuel vapor. With the cold isooctane, the air gets in. All right, so I need to wrap up because we're at the hour mark. But so yeah, you can take a one-dimensional correlation for flashing water flow and use it to close CFD codes equations. And after doing this for 20 odd years, I cannot really tell you why we've gotten such satisfactory agreement out of that one correlation without adjusting the constants. The stepped holes, we saw a remarkable ability to manipulate Sprangle through this, what appears to be a transonic expansion. And then we also saw that when you've got a surface to exaggerate the angular momentum in those holes, you can get very wide Sprangles and this switch to a hollow cone spray. That was very unexpected. So I'll just leave you with the acknowledgments, the people who provided money, computing time, and Dr. Duke and the Australian Research Council for making my visit possible. Thank you.
Thanks, David. I'll open up the floor for questions, but we'll take questions from the online audience first. If you have anything to ask, please unmute and go ahead and ask a question. You can put it in the chat if you want to.
Can't believe how fast an hour went by.
All right. Meanwhile,
Slowly for you though.
Meanwhile, we'll take any questions we have from the audience sitting in the room. Yep.
Yeah. Yep.
Thanks. So thanks, David. So perhaps dangerous question.
Yeah.
It's pretty obvious that having a finite timescale rate of phase change is much more physically accurate in a lot of these cases than having frozen equilibrium or homogeneous equilibrium. The dangerous question is it the case perhaps that simply having any kind of finite rate change is better than not having it?
Yeah.
It's just that the solution is not particularly sensitive to what that, I mean, maybe the order of magnitude of the time scale, but maybe, you know, there you could come up with all kinds of other finite, other expressions for theta, for example. Is it possible that it's just that the flow is not particularly sensitive to what it is? I don't know.
Yeah, it is possible. I just, you know, back. Right. So let's say you get pretty hot here. I think it's definitely true what you're saying here. For the cooler temperatures, yeah, it seems to be pretty insensitive. But once you get to this point right here, where it's really hot, it seems to me that the isobars, the rate of phase change is all connected. It's got to be pretty tightly coupled in that case. There's nothing else that's governing the rate of phase change and acceleration here besides that correlation. So I mean, one thing we can conclude is it's not that maybe Downers and Posky got the right parameters.
Yeah, Aaron?
I guess it's like a follow-up to your question. Have you ever run simulations changing that equation?
Yes. So in 2012, we published a paper where my grad student made an input mistake and did change those constants. So I said we didn't adjust them. We didn't adjust them on purpose. And yeah, it wasn't that sensitive. But the conditions weren't that hot either. So yeah.
I think one of Kaushik Saha, one of the guys from Argonne, the CFD guys, I think he published a paper where he varied.
Yeah.
He also tried varying the constants, and it's like, lo and behold, the ones that we were using were already good.
Yeah. Now, one thing is, so yeah, this model was put in the commercial CFD code, Converge. I wrapped this pressure solver around this correlation, so they're very tightly coupled. When they bolt on this correlation to a commercial CFD code, they don't do that. You're not going to change the fundamental pressure velocity coupling in a commercial CFD code. And so you've got a looser coupling. And I think the implementation in the commercial codes gives very different results to this. And so I think they're forced to change the constants to some degree. I mean, it's again, part of the reason that I like the open foam paradigm. A CFD code that solves every problem isn't going to be as good for your problem. So there's a lot of value to customization.
I have a question about the input flow
Mhm.
to the simulation when you put the spray, expanding, looks like Bodex breakdown, just vorticity.
Mhm.
But is the input flow axial or is it actually swirling?
It's axial.
It's axial, so what is generating the vorticity? It's swirl and
Actually, let's I've got a picture of the computational domain. If we go back far enough. There we go. Right there. So this is pretty much the domain we use. So the flow is coming straight down from up there. So you don't have any net vorticity, meaning whenever you get vorticity in one direction here, you expect it to be balanced someplace else, and it is. So the net vorticity is 0. But where does this come from? I don't know. It perhaps it comes from viscosity, right? So you always generate vorticity in a boundary layer. Yeah. But even here, right? You're passing this, you're getting vorticity that way. And then the vortex lines can interact and tangle.
Yeah, I mean, it's obviously boundable.
Yeah. And to be honest, I mean, this is a little cynical, but numerical error, there's no reason why it can't generate vorticity too, to at least seed the process.
So suggest this.
Yeah.
And also the theorems of the existing collective generation, that's what we can put out. That's the homogeneous work.
This is
It's
not.
actually vorticity being generated by asymptotic pressure and phase changes. It's a bit more complicated than
Yeah, you can
just a standard theory.
And there's also Crocos theorem, right? That a shot and an oblique shock wave can generate, although we don't really have that till further downstream.
The other interesting thing that seen in the just even simple axisymmetric nozzles is that you get when you have a non-homogeneous model, you can get baroclinic torque because grad P and grad rho go out of alignment with each other. And when your flow is turning a sharp corner and undergoing phase change, even in an axial cavitating nozzle, you can start to get a small azimuthal quantity.
That's a very good point. Yeah.
An instability.
Yeah.
Michael's created the message for you in the chat.
All right, wonderful. Yes.
Just on some like the last stuff you were talking about with the gasoline ethanol mixtures, you tend to find like compositions of
Yes, we've just been talking about that, right? So if you've got two fluids, this is distillation and how it works, right? If you got two fluids, one's more volatile than the other. As you start heating it up, you preferentially vaporize the more volatile one, and so you drive that one off, right?
time that still like compared to say if you was doing it slowly, you sort of see the same ratios of each.
Nobody knows if you do it fast, right? Thermodynamics is a misnomer. Thermodynamics really should be called thermostatics. So we only know for sure what happens if we do it slowly. Yeah. So I can't tell you with any certainty if it's different when we do it fast. You do. We don't actually output those gradients. Actually, that's what I was working on this morning. We were talking, I was like, we really need to output that. Yeah. Right, because this is important for It's the work you're doing here.
Just getting back to the case that didn't work very well.
Yeah.
Is there, that was a multi-hole.
Just up on the mic, just walk me in the screen.
Cheers. Thanks, David. Just thinking about the case that didn't work very well. Was that I maybe read that wrong? Was that sort of a multi-hole injector case as well?
Yeah, I didn't really tell you much about what it was. It was the same injector. And there was an observation plane down here and X-ray measurements and computational predictions of the mixture density, which is dominated by the presence of liquid. So it's really telling you the liquid. What was measured was kilograms per cubic meter, but what it's really indicating is liquid volume fraction.
I just wondering if you to do with, as you showed the other case with the multi-injector and the vorticity being swallowed up in there, whether it could be an upstream difference in those that could be leading to this more significant downstream effect.
Yeah, it's possible. But you know, I come back to conservation of momentum and say, how can you get the mass flow rate right and be that far off on the amount of the distribution of liquid mass? I mean, there is one other possibility, and that is that we are so completely off in the turbulent mixing of the liquid into the gas. If you think about it, right, this is fundamentally different than regular turbulent jet mixing, where you've got no big density gradients. If you are mixing a liquid with the gas, you have to move mass to spread out. If you're moving the center of mass, that requires a pressure gradient in the radial direction. That's just not there. So our simple little Fickian mixture, turbulent mixing models could be a problem.
In most of these simulations, unsteady rains.
Yeah. So actually, most of the LES runs are done by Dan. Because at Argonne, they had beautiful computers. And when we did LES runs, we did it with Argonne's computers, but most of this is about steady rains.
All right. Thank you, everyone. And thanks, David. It's great to have you here. Thanks, everyone on Zoom. We'll catch up in the next seminar, probably a couple of weeks' time. Thank you.